Hello, welcome to Chapter 3, Section 2, Using Algebraic Methods to Solve Linear Systems. We're going to do problems 10, 11, 12, and 13 on page 194. We are going to classify these systems using the words consistent, inconsistent, and dependent, independent. And then we're going to figure out what the number of solutions are. Now I did this, well, come back to that. I did this in the previous video where we talked about this, but I want to make it a little bit better, okay? So here's how this works, all right? The systems can be consistent or inconsistent, which means not consistent. Now, consistent means that you actually get solutions. Inconsistent means there is no solution. Inconsistent, before I'm going to talk more about this one, but I'm going to finish with this one. Inconsistent means that the two lines are parallel and they do not intersect. No intersection. That intersection, like I showed you on Desmos, is where the two lines come together and are that's where the solution is. So if the lines actually are parallel, there's going to be no solution, and we call it inconsistent. That's the only word you need to know for that one. On the other hand, it could be consistent. Consistent goes in two different directions. It could be independent or dependent. What's the difference? Independent is where you have the lines, if I graph them, intersect in one point. That usually means that they have different slopes. Actually, sorry. It absolutely means they have different slopes. Because if they had the same slope, they'd be parallel, or this. I'm going to get to that in a second. So if you can look at them and see that they have different slopes, you know they're going to intersect. They're not going to be parallel. They're not going to be dependent. All right? Dependent actually means that it is that both of the equations represent the same line. And in this case, they have the same slope and even the same y-intercept. Parallel lines have the same slope, we remember that, but different y-intercepts because they cross the y-axis at different places. If I get independent, I just get one excuse me, let me get something to drink. Throat's getting a little dry. You just get one solution. If they are dependent, you get infinite solutions. So here's my three choices. The lines can intersect like that, and that's my solution, whatever that xy is. Infinite solutions mean that you got the line on here twice. I can't draw it differently because I would draw the other line right on top of it. It's the same line. Smudge it a little bit. Over here I would have parallel lines that would never intersect. And please feel free to, when you do this, type these into Desmos. You can do that for all of them actually. All the problems that we've done so far with solving by substitution and solving by elimination are independent and, well, they're consistent because they have a solution, and they're independent because you only get one solution. All right, so here's the vocabulary that's important. So first we're going to decide if it's consistent or inconsistent. If it's inconsistent, you say no solution, you're done. That's it. There's no separation. That's it. You stop. However, if it's consistent, then you have to take it to another step Is it independent with one solution, or is the system dependent with an infinite number of solutions? So again, I'll take a picture of that so you can see it, so you can stare at it for a long time if you need to. All right. How do I actually get to work on this though? So I can use either substitution or elimination. I'm going to use elimination for this one, because if I multiply the 5 by -3, the x's are going to be opposites. Excuse me. I think I'm going to have to take a break after this video. I've been talking more than I usually do. Excuse me. All right. 5 times -3 is -15. -3 times -1y is +3y. And -3 times -3 is +9. The other equation is 15x, excuse me, minus 3y equals -9. These are the same. Look what happens. I get 0 equals 0. That's a true statement. And when I get a true statement, it is consistent. But since the x's and y's both got eliminated, this means that it is dependent. And if you look at it, negative, positive, positive, negative, positive, negative. After I multiplied this by 3, if I multiplied it by +3, I would add positive 15x, subtract 3y equals -9. You would have seen that these are the same line. So again, same line means consistent, dependent, infinite solutions. There's an infinite number of points on any line. All the points on this line are also the same points that are on that line. So that's why we say infinite solutions. Number 11, let's see what we're going to do here. All right. What I think I'm going to do is I'm going to solve this by substitution. I'm going to try 4x equals 8y subtract 56. I'm going to divide everything by 4. And I get x equals 2y. What's -56? Let's see, that'd be 14, minus 14. All right, now watch what happens. I'm going to substitute this. That was my step 1. I'm going to substitute this into here. So I get x subtract 2y equals -8. So I'm going to put 2y minus 14 in here. 2y minus 14 subtract 2y, equals -8. I'm not multiplying the x by anything, so I can drop the parentheses now. I get 2y subtract 2y, which is 0, and I end up with -14 equals -8. That is a false statement. It is not true. So that tells me that this is inconsistent, which means no solutions. And the reason why you get two different numbers here is because you're going to have, basically, if you look at it, if I put either one of these in slope-intercept form, I'm going to have the same slope but different y-intercepts. So they're going to be parallel and crossing the y-axis at different places. Okay, these are not the y-intercepts, but that tells me that they're going to be crossing different places. So that's why we've got parallel lines here, and it's inconsistent. Come on. Excuse me. All right. For problem number 12, I think I can do either thing. It looks, well, let's look at this. I might not even need to do a lot of work. I'll show it anyway, but look what's going to happen. Here's 8x. What do I add to 8x that's going to equal 0? -8. So what I have to do, I'm going to multiply this by -4. But if I look at my y's, I'm also going to get -12 here. So I get 8x plus 12y equals 60. And down here, I get negative 8x subtract 12y. So both of these, for the x and y, both those are opposite. Everything's going to go to 0. However, negative 24 times negative 4 is not negative 60. Negative 24 times negative 4 is going to be, what is that, 96. So when I add these together, I get 0 equals, let's see, 156. And that is not true. Sorry about the phone again. People should not be calling me. So this is inconsistent. This is what happens when you make these at your home. And there are no solutions. So just like last time, these two lines are parallel. All right, finally, problem number 13. Again, this one is set up nice for elimination. Maybe I'm going to multiply the fraction. Don't be scared by the fraction. Maybe I'm going to multiply this by negative 6 to make the x's eliminated. Not dropped out, eliminated. So I'm going to multiply by negative 6. So I get negative 6x. Negative times negative is a positive, and 1/3 of 6 is 2. 2y. Negative 2 times negative 6 is positive 12. Look what happened. 6x, negative 6x, negative 2y, positive 2y, negative 12, 12. Everything is going to be eliminated. And I get 0 equals 0. So this is consistent and dependent. And I have an infinite number of solutions. Now you're probably wondering, like I am, why didn't Dr. Berger throw in consistent independent? That's because every other problem that we've done, for all the problems that involve substitution and elimination, those were consistent and independent. We just didn't use the vocabulary at that time. Okay, see you in the next video.